is the best product to buy, and is there any other product that is exactly same as ours? And in the point of the company, the seller, when we propose a new product, we might want to do some marketing research, and want to know are there any product that is the same from other stores, and we may want to examine our opponent. So the task of classification the product from its image, it comes quite handy, and may be used in various purposes. So we will take a try on this problem. Our task is that we will build a model that take training data. Training data is taken from Shopee with various product image, and its label is like class. We have many class and a lot of image, so our model will learn from those data, and when we give the trained model a new input, like a new product of us, it will be able to tell us what type of the product is, and the class, the label group of that product. For example, if we input an image of the shoes, Jordan shoes here, it will tell us that that image is the Jordan shoes, and give us the other members of the class, like those results are also the Jordan shoe, as the same as the input, and that is what we are going to solve. However, first to solve this task, we will proceed through some steps. The first is that we need to do some data analysis to get a better understanding about our training data, and those data is extremely important to our model, because it is the base of the model's knowledge to understand the image. So we'll get to data understanding part. In our data have a lot of image with the label group. Label group is the label code for all images, like it is the name of the group for each group of image, each class, and we have the image map to the folder, the image folder. The total classes in our data is 11,014, with only 32,000 images. And when we do some analysis on our data, we realize that the data is severely unbalanced, as we see in the figure below. There are over approximately 7,000 classes that have only one or two images, and all the rest have much more images, and it's like more than half of the classes is lack of training data. So this severely unbalanced will cause very big problem to our task. And on the right hand is the visualization of one class. One class with there is 18. One class with 18 images. And they are all the same products, but in different display. And we need to classify the input image into one of those classes. And as discussed, our class is severely unbalanced. So to solve that, to like reduce the harmful effect of this unbalance, we need to do some data pre-processing, and the most important is augmentation. We will from one image of input of training data, we will transform it in various way, like rotating, translation, and change color, change resolution, to make the data more diversity and better to train. But however, this is only the augmentation by transforming image. It does not change the image content. So it is not an optimal augmentation method. But because we are not changing the image content or creating new absolutely new image, so our model is still persistent with new noise type, like background changing or image deformation. And then to approach this task, firstly we think of some neural network called DenseNet, and in the case DenseNet 134. Intuitively, we come to the DenseNet because it is proposed to have features of strengthening propagation, and it optimize the feature flow, the feature and the flows of information. So because our training data have a lot of group, as we see here, we have a lot of group that only have one training image, one training image only. So so we need to optimize the performance on only one image to train, so that we think the DenseNet could perform well. And I will briefly explain the structure of DenseNet. The DenseNet is a structure with with some dense blocks. It is the image is transformed through a convolution in every spoon at the beginning of the structure, and then the structure's body have 2 to 3 to 4 dense blocks. Those blocks play the role that they concatenate the layers, the channels. They concatenate the channels, and makes the feature, the flow, the information flow become dense, and then transport it to the transition layer and to the next blocks, and continue to the last pooling layer, and then the linear layer is to do the classification action. And in the dense block, there are sub layers called the bottleneck they are the component of the dance block that we saw it bigger here. This is zoom and a zoom visualize of a dance block. Each convolution 1 and convolution 3 here make together, they make a bottleneck, and each dance block has several bottlenecks that connect together here. Like it is the the input features, they come to the dance block, and then the output of the bottleneck is transport to the next bottleneck. Why? In the same time, the number of the input output will be transformed to on other next bottlenecks. It means that we concatenate, we do not abandon, or we do not get rid of any data, but we still keep them on and make it dense. That is the meaning of dense net. Make it dense here.
I have a question.
Yeah.
I mean, you have the sub image on the left. I mean, is that a zoom in of the dance block?
Yeah, this is zoom of the dance block.
But in the smaller dance blocks, one you have 1, 2, 3, 4, 5 cycle, right? And
Yeah.
in the zoom in dance block,
Oh,
1, 2, 3, 4, 5, 6.
yeah,
So
I understand.
what? Yes. Also
This
for the
is
connection, yes.
uh,
So
I want
between
to
color
explain that each.
blue and red, yes.
Yeah. The I'm going to talk about it just in time. The blue arrow here means that they are those two layer are one sub layer of the dense block. It means that the bottleneck has two layer. The bottleneck has two layer of convolution. Here, this is one bottleneck. I will draw it. This is one bottleneck. Bottleneck 1. And this is bottleneck 2. Each structure, each mini structure is represented by one circle here. There are one circle here. Is that clearer? And the blue arrow means that the information is still in one mini structure, and the red arrow is those arrow here that they flows to other mini structure. Uh, uh, and and uh, and when the feature is flow through those structure, they does not drop anything, but they keep sending keep like connecting the feature to the next sub layer, the next bottleneck. And so at the ending bottleneck, at the tail bottleneck, it will have a very large number of out channel. Yeah, and then the output of the last bottleneck will get to the transition layer, and then like a refresh and continue to the next block 2. And the transition layer is a convolution with and a pooling. This convolution will have the out channel of a fixed number. In our case, is 60 to 64. So after the transition layer, the channel still have the input. The next dance block will have the input of 64, just like the other dance block. Yeah, and it only make dance in the last sub layer here, sub block here, and then the linear will do its task of classification, and we will get
the mapping in the connection between the small dance block one and the bigger version of that dance block.
Sorry, can you ask
And the
again?
connection between the I mean the cycle. I don't think
This cycle.
I don't know the small cycle inside the dance block
This
one.
here.
Yes, you have the collection to the yellow, the red, and the
they all connect to those gray, zero, and red
in the
circle.
bigger version of the dance block one, I only see residual connection from convolution 3 to convolution 1. You see?
Yeah, I mean, this is one circle. It is on the circle.
One circle.
Yeah, and the output here is actually the output of one circle here.
Yes.
Go to the input of the next circle. Yeah.
And how many circle is there?
It depends on the configuration. We can have like in our model, the one each dance block has 6 to 12 circles.
Okay, so that means that in the bigger version you have that the 3 circle, right?
Yeah. It is just the explanation. And then we will next proceed to the configuration of our model and our training. For the dance block, for each dance block, we will have 3 dance block. With the first have 6 mini circle. I have said before, 6 bottleneck. The second have 12, and the last has 6 bottleneck sub layers. And the growth rate equal to 32. It means that after each of the circle here, after each flow of the mini layer here, the number of our channel will stack will be increased by 32. That is the growth rate of the model. That is two most important two most important information about our model. It defines the structure, and for the learning rate and the loss, we use learning rate initially of 0.01, and the learning rate must be decreased by smaller in time, or otherwise it will not convert. It will not get better result. That is what we see in the training phase. And the input shape is of 64. That 64 is the batch size, and 3 is the number of color channel, like black, blue, green, red, and 96 is the image size. That is resized to reduce the number of parameter and still be runnable by GPU, because when we try with larger image, the number of parameter increased dramatically, so it caused the RAM to crash. And we use cross entropy loss to calculate the accuracy of our model. But we will discuss about the result later in evaluation part, but I will spoil a little that the dense block, the dense net here is not does not work as we expected, because there are maybe two main reasons. The first is that our data is severely unbalanced. So the data for training is not sufficient for our dense net. And the other reason is maybe because that it converts really slow, very slowly, and it takes a lot of time to train. So because the dense net does not provide the expected result, and then we approach the problem in a different way. That is because the dense net have the hunger of data. It means that the provided data is not sufficient to train, and it will not it could not classify other classes rather than the given one, the given 11,000 ones. It will not know about other classes. So the DNSNet have many disadvantages. So we want to approach in a different way called the embedding model using chiplet loss and another approach. This SciMainNet will be presented by Phạm Thanh Hưng in the very next session. Hưng.
Okay, so I will continue the presentation of our group. Can you guys hear me clearly?
Yes.
Okay.
Okay. So I will share my screen. As Nhật has presented to you about the DenseNet, this is a traditional approach of a model for classification problem. So the downside of this approach regarding to our SOPI dataset is hunger of data, and it cannot scale, which means unscalability. So we want that the number of image per class is sufficient for 11,000 category without overfitting. And we also want that the model is capable of discerning new type of product without much effort to retrain. So for this reason, and plus the fact that our SOPI dataset is very lack of data, we propose a second approach. It's CMESNet. It's an embedding model. And in terms of the idea of this embedding model, it seems like it's performed very well in the problem of few shot learning, and it requires a little data, but still can achieve a state-of-the-art performance. So let me explain how it works. First, this is as I said, this is an embedding model, and it's not produce a, a prediction, but it produce a vector, embedding vector. So as you can see in here, we have the term triplet loss. So this loss is different from other model because it uses 3 images to compute. So the first one is we call the anchor. Is basically every random image in our data set. And the second one is negative. This is the image that this is positive. This is an image that's the same class with the anchor. And the third is negative. It's the image that have different class with the anchor. And we input all 3 images to our model, and we acquire the embedding vector for each image, and we will compute the distance between each of these vectors by using the L2 square distance. And our goal is to make the positive closer to the anchor and the negative is further. And this is the algorithm for the loss of embedding model. So about the type chiplet, because we have to map 3 images together for training. What kind of image we can choose to be a chiplet? We have 3 kinds of chiplet. The first one is easy chiplet. Second is semi-hard chiplet, and the third is hard chiplet. This is based on this convention is based on the position of negative. So this is you can see in this image, this is the anchor, and this is a positive image. So the negative one, when it lie on this area, which means that the distance between anchor and negative is smaller than anchor and positive. So we call that hard negative. If the negative remain in the orange area, it will in the margin, and when it lie on outside of the circle, it will be the easy negative, which the distance of that image will larger than the distance of positive to anchor. And since the easy negative is make no sense for training, because the loss is of easy negative is 0. So we just choose the hard negative triplet and semi-hard negative triplet for our training.
Is there anything wrong with the hard chiplet? You write DIN smaller than the DIP.
It's not. It's true, teacher. Because as I explained, this is the one that have the highest loss for the model.
Really?
Yes, I think so. Because when the negative is smaller than the positive, so it means our model is not good and the loss is very high. So we need to optimize this area to make it to easy negative.
How do you calculate the loss with the hard chiplet? What is the formulation for the loss?
This is the formulation. We will this is the distance for the positive, we will minus the distance negative, and plus the alpha is the margin. So if the position, the distance of negative is smaller than the distance of positive, so the loss will be positive. So which means it's not good, and we have to minimize.
So you have DP, DN. Can you move to the next slide?
Yes.
So what is the DP in this case, and what is the DN in this case?
This is DP.
This is
and
DIP is the DP, and DIN is the DN.
Yes.
What do you mean with DN is smaller than DP? Wow.
I mean, like for example, I have 3 images, anchor, negative, and positive. So when I compute the distance between those, the 2 images that have the same class.
I understand. Yes. Can you move to the next slide? Yes, I mean, it's not consistent. I mean, the way you say hard chiplet, and on the image you have hard negative and semi-hard negative, and here you have semi-hard chiplet. I don't understand.
Okay, so the hard chiplet is mean that the negative is lie on the area of hard negative, and the semi-hard that's the way we call based on the position of negative for the chiplet.
Okay, let's move on.
Okay, for the training process, we will the first one is the architecture. So there's a lot of architecture for classifying image, but we choose MobileNet v3, which is pre-trained on ImageNet to be our main architecture for this embedding neural network. And the reason is because it's very lightweight, as we have very low resources in Google Colab with very small like GPU and RAM. So we choose this as our architecture, and then we fine-tuning the model. There are a lot of parameters for tuning, but the most important one is the batch size. The reason why we have to focus on the batch size is if the batch size is too small, so it cannot. If the batch size is small, so it must converge because in terms of stochastic gradient, and in other side, the batch size should be large to find good semi-hard chiplet. And because we have limited resources, we just tuning for two value. The first one is 64, chiplet is 64, and second one is the batch size is 128. And as you can see in this figure, the batch size of 64 have the loss is smaller than the 126. And about the learning rate, we use the initial rate is 8e minus 3, and the momentum is 0.9. The output layer, which is the size of the embedding vector, is equal 256.
Why do you think that the most important hyperparameter is batch size? Is there anything else?
Because the batch size is, if the batch size is small, so it must be quite small, because if large, it will cannot converge, and if too small, it will have very little.
So you mean that there's some relationship between the batch size and the loss?
Sorry, can you say that again?
You said that, I mean, can you say your argument again? I could not understand.
Okay, so when we train the embedding model, we have to make chiplet, right? And when the process of making chiplet is that we have to choose instant image.
Yes.
And if the batch size is too small, the variety of chiplet in each batch is not too good. It must be large enough to have both semi-hard chiplet and hard chiplet. But if it's too large, it cannot.
In the formulation for the chip loss calculation, you just mentioned three sample, right?
Yes.
And here you are discussing about the batch size. I don't. Can you, I mean, reformulate the loss again to include the batch size parameter?
Uh,
See,
Can you hear me?
yes.
Because in order to compute the loss, we need to have chiplets. As we said earlier, we want to find the good chiplets, which is the hard chiplets and semi-hard chiplets. But how to find the good chiplets? Because our class is very huge, but there are very little amount of data per class. So for our 11,000 classes, we have at least 60 million chiplets. And in order to find the good chiplets among all these 60 million of chiplets, we will need 360 hours to train for one epoch, and that is not enough time. So we have to reduce the search range from the whole data set to a small epoch, to a small batch size, to a small batch. Yeah, yeah, you understand me? We need to find good chiplets to update, but we cannot use all the data set to generate chiplets. So we just able to find good chiplets among a batch.
I mean,
So
for
if batch,
right? Okay, right.
yeah,
Understand. But I mean, why is different? I mean,
because okay, uh, if the batch size is small, then
yes.
we are following the effect of stochastic gradient descent, which means if the batch size is small, we are ensuring the problem is able to converge to the global minimum of as in the theoretically, right? But if the batch size is too small, then our search ring is also small. Maybe we cannot find good chiplets.
Okay. So, is there any other parameter that is good to consider?
Um,
yes, yes. We have this is just a training process, and when we train, we have another parameter to deal with because we have to classify the image using KNN. So there's another parameter for tuning is
No,
the
I'm
number.
just asking about the CMNS training. Can you go back to the previous slide? I mean, is it I mean, possible to evaluate the number of layer that you are unfreezing? But
I
you
think
just you freezing just a few interior layer. So how good is a few? 1, 2, 3, 4, 5, 6, 7.
We freeze about 20 first layers.
Why? Did you do any experiment with that number?
No, we don't have chance to practice with these numbers because the limited time. And the reason why we choose the very little amount of layers because our class is very different from ImageNet. Because our problem is mostly about the shoes or something like pants. But I see when I investigate the ImageNet is mostly about animals or something in nature. So the distribution is very different, and we have very little amount of data. So we just can do fine tuning for a few first layers. Actually, we plan to
How many
test.
layer do you have for the mobile net version 3? How many layer you have?
Uh, we don't remember, but because the MobileNet V3 has shown a very good performance on the benchmark of ImageNet, so we just employ it.
Yes, but the thing is, I mean, the number 20 you choose must be based on some reasoning, right? I mean, it's 20 hour of something. So I just want to understand what is the total number of layer in that MobileNet version 3. So say if 20 is small or 20 is too big.
When we when we freeze the number, totally the number of parameters in the MobileNet V3 is it is 3 millions parameters, and we just freeze for one 1 million, which means one third of the parameters.
Do you think it's too much or it's just the right number?
We take that number because it's intuitive in our mind. Actually, we were planning to tune this number of the freezing parameters, but we don't have time. To be honest, actually, we want to tune a few more parameters, but we don't have time. For example, the batch size, we want to tune it for 256 image per batch, but we could not because we don't have time. And we really sorry for that. We just can tune batch size for 64 and 128.
Okay, so let's go on.
Okay, so after we train our network, we choose that the batch size is equal to 64, and the number of epoch is equal 30 epoch, and to get a visualize of the model after training, we have here the demonstration of 80 classes. This is we using PCA to map from 2,056 dimension to 2-dimension space. So you can see each color is each class, and it's very quite obvious. About the classification phase, after we have embedding vector, we use KNN to classify with the number of class that, like what I said before. So when we increase the number of nearest neighbor, the top 5 accuracy increase significantly from 0.46 to 0.51, and the top 1 accuracy is not decreased, but not too much. So eventually we choose the number of nearest neighbor equal to 14. So about the evaluation phase, we have 2 models, and the inference time of DenseNet 134 is faster than embedding CMA model. About top 1 accuracy, the DenseNet is 0.07, which is quite not too good, and the CMA net is 0.45. Top 5 is witness a same patterns, that our highest accuracy is 0.51. This is if you look at it, it's quite bad, but but in comparison to the benchmark of MobileNet, we noticed that the MobileNet achieved about 0.7 accuracy on ImageNet, which is the dataset have 1,000 classes and 1 million image. But in the meantime, we have 0.51% accuracy on a dataset have 11,000 classes with just about 32,000 image. So I think this result is not too disappointing. And the DenseNet 134 can still be enhanced and improved by if we have more resources for training, because we train it about 20 hours on Google Colab, but the data is not too good and it takes a lot of time to convert. So maybe in the future we can tackle this problem and increase the accuracy for DenseNet. So about conclusion, the problem of shortage in data has prevented us for achieve high accuracy and in general to get close to our goal. But we have implement a model that is perform very well in few short learning problem, and most of the model we implement are very potential to become our standard solution for image classification with a data set of few short learning. For future improvement, we will need to enrich our data by collecting more image for each class, and we can thinking about applying generative advisor network for generate new image. Also, we want to try other architecture and that is robust to class imbalance. So that is all of our project. Thank you for listening.
Okay, thank you. So I have two questions to clarify my understanding of the work of the group. So can you go back to the slide number 8? Number 8. Yes, that's one. So can you explain again what is the growth rate in this training configuration?
The growth rate here is like we have said before, each dense block have have in the configure have 6 and 12 and 6 bottleneck sublayers in this mini structure. Do you remember? Each dense block have 6 bottleneck here. So the growth rate is actually the output of the bottleneck, but the difference is that we do not we concat the number of channels through each bottleneck, so that after the first bottleneck we have 32 out channels, and after the second we have 64. After the third we have 96. Like if you roll by the number of 32 after each bottleneck sublayers.
Can you explain again?
I will share my slide so I can
Okay.
Yeah. The growth rate is the output of one circle here. Each circle here. The first circle have the output of 32. And it the output will flow to the second. The second sub layer here will also have the output of 32, but it will concat with the output channel of the first one. So the total number output here is 2 times of 32, it is 64. And similarly to the third and the fourth circle, it will stack, it will accumulate the output here, stack, but not drop or not override it. It's stacked together. So after each node here, the thickness or the length of the block is increased by 32. It means the growth rate of the model.
Okay, so go back to the slide 6.
Yeah.
Yes. So what is transformation? Review for the data preparation. Can you enumerate the transformation?
Yeah. Our transformation include rotating, flip, and color shift and hue shift. And in the DenseNet config, we will use additionally transformation of cutout. Here, the transformation is rotation, translation, color adjustment, scaling, cropping, flipping, and padding. Do you have any advice or any suggested improvement for our DenseNet or Fusion Learning here?
I have another question about the data collection.
Yeah.
Yes. So
our data is collect from Shopee, from Kaggle.
Kaggle.
Yeah.
So it's somebody else that collect the data and they post in Kaggle.
It is actually data posted by Shopee. Shopee hosted a competition.
Okay, so Shopee hosted the
yeah. It's not.
Okay. So what is the state of the art result for this challenge?
Still our result is most reaching by embedding model here, but we have seen some top result of the competition. They have reached the 96%. So I think it's far more for us to develop.
Okay, so thank you. Maybe we can take a break of 5 minutes and we go to group 3. Okay.
Okay, thank you.
Okay, so let's continue with the presentation of the group 3.
Teacher, can you see the slide? Thầy nghe rõ em không ạ?
Yes.
Vâng, thầy thấy slide đúng không? Em...
Em bắt đầu chưa?
Yes, em có thể bắt đầu.
Vâng. Hello everyone. Today we would like to present our project about Vietnamese sentiment analysis. Our group have 5 people, which are Phạm Văn Cường, Nguyễn Việt Hoàng, Hoàng Văn Khánh, me, Phan Đức Thắng, and Phạm Việt Thành. Next slide, please. In this project, we will build a sentiment analysis system based on the UIT VSFC dataset, which contains the Vietnamese student feedback on various topics from Ho Chi Minh University of Technology. For the given dataset, we choose to implement 4 models to see if we can achieve a better result, which are INN, LSTM, Transformer, and BERT. Now I will present about the overview of our dataset. So a dataset has 3 classes, which are negative, class 0, neutral is class 1, and positive is class 2. As you can see, our dataset is very imbalanced. The number of samples in the negative and positive polarity is much larger than the number of samples in the neutral class. And next, the second is the set length distribution of data set. As you can see, the distribution on the slide, most of the sentence has a length between 10 to 40 words. So this will influence our choice of a sequence length to implement in our INN and LSTM model to part. And next, Cường will present to you about the pre-processing data and the INN model.
Okay, so for pre-processing, because the data set is already cleaned by the author, so the next important thing we have to take care is the data representation. So we use these 2 main ways of representing data: one-hot representation and word embedding. So one-hot, most of you already know what it is, and word embedding, we make a tokenizer encoding of the sentences, and then pass them into a embedding layer at the start of each network. And also, one thing we want to note here, that we added some special tokens to our vocabulary. First thing is the name token to represent human name. The second thing is the unknown token to represent words in def set and test set that don't exist in the training set. The path token is used for padding, and also we didn't remove the punctuations because punctuation in Vietnamese sentence contribute somehow to the overall sentiment of sentences. So next slide. Okay, so another technique we apply is the word segmentation. So we already know that words in Vietnamese can contain 1 or more syllable, as you can see in the example on the slide. So for example, a 6-syllable sentence, tôi là một nghiên cứu viên, forms a 4-word sentence. So here, nghiên cứu viên is a compound word, a single compound word. And also to do this, we used the RDR segmenter from VNCore NLP. So next slide. So the first and the most simple model we used in this project is recurrent neural network, RNN. So because we already learned about RNN in our course, I'll go through this really quick so we can save some time for more interesting stuff. So here are then we for this problem, for our particular problem, we use the many-to-one architecture of RNN, and only the last output of the output cell is taken into account. Yeah, this will be in the form of a probability vector of 3 dimension, because we have 3 classes, and this probability will be used to make prediction. So next slide. And also to improve performance of a recurrent neural network, we can add more layers. So we use a 3 layers RNN model. So next slide. So this is the performance of RNN on the development set with different settings. And as you can see, RNN alone can achieve about 88% accuracy. Not so bad, but not so particular, not so spectacular either. And after tuning, adding more layers, using word embedding and word segmentation, we can improve the results significantly. And by tuning, we tune the hidden layer size, the embedding dimension, the learning rate, and most importantly, the length of the sequence. So yeah. And as you can see, okay, so now Thắng will present to you LSTM.
Okay, so the main difference of LSTM is that it can have a forget gate and the output gate that we have already studied in the class. So I will only talk about our specific implementation. So our first approach here is that we only use the final output of the final cell to fit into the linear layer to predict the label. However, in this approach, the information from all the previous work have encoded into the final cell, so it's not utilized effectively. So we come up with a second approach, which is we add all the output of all the cell and to fit it into the linear layer. In this way, we hope we can utilize all the information from all the word in the sentence. So now I will compare the result of the two approach. Here is a graph of our changing loss over time. So as you can see very clearly, when we use the sum of the output to predict, the model converges much faster. And next is the results on the depth set. So as you can see on the here table here, the F1 score of the neutral class is higher if we use the sum output. It's significantly higher. So we conclude that the sum is a better way of the when we don't compare to when we don't use it. And we also tune other hyperparameter. For example, here we found out that non-bidirectional is the best hyperparameter, and with a sequence length equal to 40, and embedding layer is better than the one-hot representation with a layer dimension of 500. We also compare the performance when we don't use we use code segmentation compared to using word splitting only. So as you can see, the accuracy and the overall weighted average of F1 score is higher when we use word segmentation. But interestingly, the F1 score of the neutral class is higher when we don't use the word segmentation. And next, Huang will present about the transformer.
Okay, so since the transformer is not included in our course, I would walk through the original model first. The transformer has the encoder and decoder structure. The encoder would map an input sequence to a sequence of abstract representation that holds all the information of the input. Then, given the encoder output, the decoder would generate an input sequence of symbols, one element at a time. Also, the previously generated symbols would also be used by the decoder to generate the next symbol. The transformer uses the scale dot product attention, which involve with three kinds of matrices: the query matrix, the key matrix, and the value matrix. The formulas for the output is calculated as you can see here. One point that we're noticing here is that the dot product of the query matrix and the key matrix is divided by the square root of the dimension of the key matrix, which in order to avoid the vanishing gradient, the transformer uses the multi-head attention mechanism, which includes several parallel attention layers in one encoder or decoder. Next slide, please. As you can see in the figure on the right, in each encoder or decoder layer, there is a pointwise feed-forward network. This feed-forward layer consists of two linear transformations with a ReLU activation in between. Also, we use the learned embeddings to convert the input and the output into vectors of the same dimensions. To add information about the positions of each token in the sequence, the sine and cosine functions are used for the positional encoding. The formula is shown on the bottom here. The post refers to the position of the word in the sequence. The D model means the size of the embedding, and the I letter refers to each of the individual dimensions of the embedding. That is, it can be 1, 2, 3, 4, up to 512. Next slide, please. Since our task is sentiment analysis, so our model only contains encoder layers. Also, the linear transformation and softmax functions are used to convert the encoder output to the final output. The table at the bottom of the slide, that it shows the hyperparameters that we have tuned. Those are the input and output dimensions, the embedding dimensions, the number of heads in multi-head attention, the number of encoding layers, and the dimension of the feed-forward network that we have discussed above. There is one point that worth noticing here is that the input and the output are, for each sentence, would be equal to the number of tokens in the chain data's longest sentence. Next slide, please. We used for the transformer, we try two data sets with two different types of preprocessing. One is word splitting, which is to split sentence into tokens based on the specs character. The other technique is word cementing, which has been described by Cuong in the processing part. Additionally, we apply the pre-training technique called the masked language modeling. The task is to give the model a sentence and then optimize the weight in order to output the same sentence on the other side. While the input and the label sentence are essentially the same, the input sentence has some of its token masked. The bottom table shows the model's performance on the validation set. This model uses the tuned hyperparameters. We can see that the model that is trained on the word cemented data has better performance than on the word split data. Also, the model with the pre-training does provide better results than non-pre-training model. That's all for the transformer. Next, Thành will discuss about the BERT.
Okay, so in this section, I will briefly explain the BERT architecture and its training objectives. So firstly, BERT uses the transformer architecture that Hoàng has described above, and as being originally designed for language modeling, BERT only includes the transformer encoders and ignores the decoder. As you can see in the figure, the input to the model is a pair of sentences. In the original implementation of BERT, a sentence here is not a true linguistic sentence, but it is a segment text sample from the data. To distinguish between the two sentences, a set token is placed at the end of each sentence. And additionally, a CLS token is placed before the first sentence, which will be explained later. This is the input representation when putting into the BERT model. As you can see, we use 3 embedding techniques and finally add them all together to form the final input. The first embedding is token embeddings, in which BERT use the word piece tokenizer, which is similar to BPE, which broke the word into subwords. The second one is segment embeddings, which are binary numbers that tell which tokens belong to which sentence. The final one is positional embeddings, which is just similar to transformer. BERT has 2 training objectives, and it is optimized simultaneously. The first one is the mass language modeling, which is previously described in the transformer section. And the second one is the next sentence predictions, which is a binary classification problems. It uses the hidden state output of the CLS token and pass it through a binary classification loss. Now we will discuss a modified version of BERT, which is used in the ISIS project, and that is Roberta. Firstly, Roberta performs dynamic masking, which changes the mask of the sentence whenever the model sees the sentence. While in the original implementation of BERT, the masking is performed only once in the data preprocessing step, so the mask position is kept and remain the same. Secondly, Roberta removed the NSP objective, so the CLS token is not used for anything. And because we cannot use the CLS token for classifications, to use this model for sentiment analysis, we have to append a linear layer on top with random initialization. This is the result of BERT on the development set. From the first look, we can see that BERT without pre-training has really low accuracy and F1 score, just about 91%. When using FurBERT base as the pre-trained model, we are able to increase the scores by about 3%. And we also try to fine-tune the FurBERT without using word segmentations. And overall, the result is only slightly decreased. But in the neutral class, there's a big increase, which is about 8%. Finally, we also try to fine-tune the FurBERT large, which is 3 times the size of FurBERT base. And as you can see in the table, the results didn't increase much. With the results like this, we can see that the pre-training can handle the problem of domain mismatch, because FurBERT was trained with text from newspaper, and our data is student feedback. Now we will discuss the results of all the models after tuning on the depth set, and this is the results on the test set.
So this is the result that we taken from the test set. Each model below here is the configuration that achieved the highest result on the depth set when tuning. As you can see the bold line in the screen, BERT is the best model on the test set. Following that is Transformer, LSTM, and INN model. However, you can see that the neutral score on INN is quite bad compared to other models. So we try ensemble learning only using Transformer, LSTM, and INN model to see that if it can push the result further on weaker models. About the BERT ensemble, you will see after this part. So let's come to ensemble strategy. So the idea of ensemble learning is to combine the output of individual models into a single output of ensemble. So we have 3 trained classifier, which is Transformer, LSTM, and INN. Each one achieving about 89 to 93% accuracy. A first simple way to create a better classifier is to aggregate the prediction of each classifier, and then we predict the class that gets the most vote, as you can see the picture on the slide. This majority vote classifier is called a hard voting classifier. Our transformer model only does a slightly better result than INN and LSTM, but thanks to the law of large numbers, we hope that our ensemble prediction can be a bit better. The second way to create a better classifier is soft voting. Next slide, please. The soft voting that predicts the class label based on the argmax of the sums of the predicted probability of each model. And we believe that the soft voting, aka average voting, can improve on hard voting because it takes into account more information. It has presentation on 3 labels. Next slide, please. Overall, the best ensemble model among this model, as you can see, that is the LSTM along with the transformer. This model improve the result significantly on soft voting strategy with the word segmentation data. And compared to the best transformer configuration, this ensemble model can increase up to 0.5% in accuracy and with the average F1 score. And now you will see our further improvement on BERT ensemble models.
As shown in the previous slides, the BERT actually already achieved a pretty high result, but we can still improve it more. So we'll try 3 different training strategies. The first model is trained without preprocessing the names. The names here refers to the names of a person or name of the companies. So the first model is trained without preprocessing the name and just keeping them as they are. The second model is trained with the data in which all the names are removed. The final model is trained with the data in which all the names are replaced with the name tokens, just like other models, INN, LSTM, and transformer. The table shows that model 3 achieved the overall highest result, while model 2 achieved the best F1 score on the positive class. With these 2 models, model 2 and model 3, we will try to perform some ensemble strategy to see if we can increase the result even more. This is the result of our ensemble on only using the BERT. The first line in the table is the previous best result, which is from model 3. After the experiment, we find that combining model 2 and model 3 achieved the overall highest accuracy and F1 score. Finally, we compare our result to other papers that also do research on the same dataset. The first line is our best model, which is the BERT ensemble before. It achieved the highest result of an unweighted F1 score of about 94%. Another paper that used the ensemble of different architectures, BERT, CNN, BioSTM, and LSTM, achieved an accuracy, an F1 score of more than 92%. The last one is the results from the paper of the dataset that we use. The results seems a little bit low because the authors only use a simple model, which is max-n. It is a statistic model, so it may not generalize well. In conclusion, we see that using the word segmentation improves the performance of every model. And by applying ensemble mechanisms, we are able to increase the performance of BERT and other models too. In the future, we hope to achieve an equivalent or better results on other Vietnamese sentiment analysis dataset. And we will try to experiment with adding in-domain pre-training data for transformer and BERT. Because we use Colab, and if we try to pre-train from scratch, it will take a lot of time. Thank you for listening. Now come to the Q&A section.
Okay, so I see a first question in the chat. Gatvu asked us, okay, so what is the name token, right? So yeah, I will send it into the chat also. An example of the name in the data set. So the authors already clean their data and they change all human name to this. Did you see the image? Yeah, they changed the data into this kind of code. And for example, this WZJWZ209, this name only appears in the data set only once. So we change all of these name into a single name token. So yeah, do you have any other question? So I see another one for bird large. Yeah, Thành can answer.
Okay. I see. So I will come back to the result of Verbet large and Verbet base. As you can see, Verbet large only increased the result by very little bit because the training data set is pretty small and the Verbet large has really many numbers of parameters, which is about 300 million parameters. So I think the loss signal is not significant when using a small training data set. Maybe the result would be better if we use a larger training samples size.
Any other question? Hello.
Oh, another one from Vu. Okay, so in the ensemble model, why combining two birds with different strategy? Okay, Thành, can you answer this?
Yes. So I will come back to the slide. Okay, so model 2 is trained with all the names are removed, and model 3 is trained with all the names are replaced with the name tokens. The reason model 3 has better performance than the base model, which is model 1, because the name tokens is already see in the vocabulary. While model 1, if you not pre-processing name, so it will count as unknown words, and it will be by the word piece tokenizer, it will be broken into character tokens. It is the same case for model 2, so it removed it has the less number of our vocabulary word. So and additionally, we can see that each model has its own advantage. Model 2 has the best F1 score on the positive class, while Model 3 has the best overall result. So we combine this by ensemble to, and hope that we can increase the F1 score overall.
Okay, so I have some question for the group. Can you compare the burst and the transformer model? In the slide, you said that in the transformer model, you just use the encoder, and the encoder is actually burst, right?
Yeah.
So why do we see the differences in terms of performance between the transformer and the burst?
Because the transformer was pre-trained only with the student feedback data set, and in the BERT model it was used the Verbert pretrain, which was pretrained on about 20 gigabytes of text. So yeah.
Okay.
Oh, there is another question from Trường Giang. Can the ensemble model run on edge device? And how many parameters are in your best model? Okay, so for ensemble, we doubt that they can run on edge device because while the performance is higher, but the inference time is higher as well. And for edge device, that maybe not very ideal. Yeah.
Yeah, I can add more to this. The best model, which is the best ensemble, is model 2 and model 3, which has the total number of parameters of about 2 million parameters. Yeah, obviously it cannot run on edge device, but we can use some techniques like model quantization or distilled learning to reduce the size of the model while still retaining the performance.
Okay, can you go back to the slide when you present the transformer, slide number 17?
Yeah.
When we present about the positional encoding, so what did we mean by the 2e and 2e plus 1? 2i plus 1?
Hoàng, can you?
Okay, so with the I is I mean the I is a dimension of each
dimension of H. What do you mean by dimension?
No. Let me say the position of the individual dimensions of each of the embedding. So this is I mean so you want to ask why there is the 2i plus 1 in the formula, right?
Yes.
To be honest, this positional encoding is from the original papers by the Vaswani. So we only implement the positional encoding and
you implement, but you don't understand why. No, I don't think you implement this. That's some code from somebody else, I'm sure.
No, there is okay. So okay, sorry, I cannot answer properly for this.
And again, for the for the attention for the encoder on the previous slide, level 16.
Yes.
Yes. Could you elaborate a little bit about the QKV? I mean, what did that mean? QKV.
Okay,
I mean,
so
I mean QK and V, but I mean, why is that? I mean, why the scale dot production attention is calculated that way? I understand the softmax. Okay, per softmax you convert, I mean, everything inside to be the probability, right? But why is QK, and then you divide by the, I mean, square root of DK, and then you multiply with V. See?
First, for the division, for the divide by the square root of DK, is in a we use a softmax here. So we all know that if the result of the dot product is too large, then the gradient would be small. So the deviation is in order to scale it, so we can avoid the vanishing gradient. And the product of query and key and the value here, I mean, there is a paper about dot. Actually, the transformer use dot product attention. It's just added to the scaling part here. The formula for the attention is in the sorry, but do you need the clear explanation about the purpose of QKV or?
Yes.
Or, yes.
The
So
purpose, meaning of QK and V, I mean.
So the let me see. QK.
And what is
So,
Q, K, and V, and the specific exam for the, I mean, sentiment classification problem?
so the Q, K, and V are the for each of the, it would be like how the query would be like look into the dot product of the query and the key in order to have different different, can I say the amount, different amount of attention to the to sub part of the sentence. That is for the value, and the query and the key are essentially the one that holds the information about the sequence.
Do you have other example to say what is Q, K, and V in a very specific example?
In a very specific. Okay, so I think in order to show that, we would have like to show.
Do you mean where the Q, K, and V come from, or?
Yes.
Okay, so Q, K, and V here are just like embedding of the input sentence. This is like a self-supervised technique. So yeah, the same sentence into an embedding layer, we get Q, into another embedding layer to get K, and another one to get V.
Mm-hmm.
And anyway, so can I re-explain the positional encoding?
Yes.
Okay, so as I said before, we use the sine and the cos. We use both of the sine and the cos. So for each token, it would have two representations, the sine and the cos. So for the token number I, in the sequence, the token number I, it would have two values. For the 2i here and the 2i plus 1 is all refers to the same token. I think that's all the meaning for the 2i plus 1 over there.
Are you sure? Are you sure about that?
For the, I mean, it's the pairs of sine and cosine. It all for the same I, essentially. As you can see here, for the PE position and the 2i plus 1, it would all be the positional encoding for the token at the position I. It would be represented by the 2i and the 2i plus 1 in the positional encoding.
So it's I mean, from my understanding, the I here just say that, okay, in the case that the position is odd number, right? Then you follow the computation number 2, and if the position is an even number, then you will follow the computation number 1.
sorry, but I believe that we use both the cos and the sine. So I'm not objecting to you, but I have read in the that it use both the cos and the sine, and there is can I show my my screen
Yes,
for the
you can
yes.
show the screen. Yes.
Yes. So I have reopened the code here as a chat. This is a vector that represents the positional encoding, as you can see here for the for each of the.
This
Yes.
is not the original paper. See?
Yes, but the original paper has very few detail about the positional encoding actually. It
So maybe it's different understanding because in the other places.
It only has a small part about the positional encoding here. Where is it? Multi-head attention scaled up product. Yeah, it just has this, and it doesn't say much since I believe that this paper takes the it's not the original paper for the positional encoding. And as I said before, for each word, it would have two representation. So for the word I, it would be represented by the 2i and the 2i plus 1 in the positional encoding vector.
Maybe we should double check in the code because in the other resource I found is like this. Maybe you can check in the code to see the correct answer.
Okay. Sorry, but can you send me the whole paper so I can read it again?
It's in the same the same resource as you.
Attention is all you need. Okay, so I would take a look over it after this presentation.
Okay, so any other question for the group 3? Okay, so I think that we can have another presentation from the next group. Hello.
Yeah, I'm from group 2, and let me say my slide.
Right.
I mean, before we end our group 3 representation, can you give us some advice or something? How did you see how did you see our presentation?
Okay, I cannot give you the I can just because I haven't checked the documentation yet. So from my point of view, after listening to the presentation, I think that you guys have a content work on evaluating different various model for data sentiment analysis problem. So at some point, I mean, for example, when I am asking about the transformer, the explanation was not so clear enough, but on the other part of the presentation, I think is quite good one. So.
Okay, thank you.
Okay, thank you. So I will share my slide. Do you see my slide and hear me clearly?
Yes.
Okay, thank you. Okay, so I'm going to present our work of group choose, and here is you can see the member of our group, and me, Trần Quốc Khánh, Hoàng Thiện Tâm, Phùng Hoàng Nguyên, and Nguyễn Huy Hoàng and Lê Đức Anh.
Maybe you can stop a little bit. I should record the discussion for the group 3.
Okay.
The guy that participate in the discussion, could you say your name?
We have Phạm Cát Vũ and Lê Trường Giang here.
Phạm Cát Vũ and Lê Trường Giang.
Ý thầy là nhóm em trả lời hay là kiểu câu hỏi của người khác?
Cả hai em ơi.
Thế thì phải thêm cả Phạm Văn Cường với Phạm Việt Thành và Nguyễn Văn Hoàng.
Em thể nói lại được không? Phạm Cát Vũ này ai nữa nhỉ?
Lê Trường Giang.
Lê Trường Giang.
Phạm Việt Thành. Nguyễn Việt Hoàng.
Ok rồi.
Phạm Văn Cường.
Ok rồi, mình thấy nhóm này trình bày đồng đều đấy. Không sao. Okay, thank you. So group 2, can you start?
Okay, so I will continue our presentation now. And our presentation contains 3 parts. The first part is about the data set and data pre-processing and the problem of our project. And the second part is the model which we have implemented. And the last part is we will talk about our results. And okay, so let's look at the data set first. And you can see in the picture here is the illustration of our data set, and we contain the industrial product image. And the first row is indefective products, and the second row is the defective products, and the last row is the image of the part which is defective. And let's look at the detail of our data set. And our data set is MPTech anomaly detection, and it had it had 15 class. For example, the carpet, grid lasers, and we have the training set and the test set. And for the training set, it only contains the wood image, which means it is defective. And the test set also contains the wood and the defective one. Okay, so you can see in the shape of the image here, for different categories, the image shape is different. So for the CNN model, we need the fixed shape that input to the CNN. So we reshape the image to the size 256 by 256. And also the image is the 3-channel image, and it ranges from each pixel is integer from 0 to 255. So we convert it to interval from 0 to 1, and we using the dot vision transform to transform it. And okay, so the second part I will talk about the modeling. And as you see here in the data set, we only have a little image, and only 5,000 images. And you know, in the nature, the percentage of the anomaly detection is quite low. So we cannot use classical CNN classification to detect the defectives. So we propose to use unsupervised learning, and the first model is the autoencoder. And you can see in the picture here is our autoencoder architecture, and the upper part here is the encoder, which takes the input image and transform in compress it to a latent space, and the low pass is the decoder, which will take the latent vector and reconstruct the image. And we use 4x4 filters, strike 2, and okay. So yeah, it's a description about the encoder and the decoder. And the goal of our autoencoder is to output an image which is similar to the input image. So we will use mean square error loss, compare the input image to the output image, and backward progress the gradient and update the loss. So the training of the autoencoder is quite simple. And one disadvantage of autoencoder is that we do not have control to the output of the encoder, and it's going only to output an image which very similar to the input image. So we propose the second model is the adversarial autoencoder, and you can see here the picture is the architecture of adversarial autoencoder, and the the upper part here is the encoder, and the encoder will take the image and output sampling from distribution, and you can see the mean here and the standard deviation. And after that, the decoder will decode the latent vector, and it is similar to the adversarial autoencoder in the past, and it's similar to the VIE we discussed in our course, but instead of the KL diversion loss, we will use discriminator loss to tell the encoder to output the latent vector that's similar to an fixed distribution. And for the training loss, for the training of our model, we have 3 phases. The first one is the reconstruction phase, which is similar to the autoencoder. And the second one is the train the discriminator to recognize the real latent or the fake latent generated by the encoder. And the last phase is to train the encoder to encode the latent that look like the fixed distribution. Okay, so one thing that I want to clarify here, the last the 129 here is not fixed. It's latent dimension, so it can be trained, and we will fine tune it. Okay, and we have fine tuning the learning rate, and you can see here is the lot of the learning rate in a bottle data set. And for the learning rate, high learning rate, it converts faster in the first step, but it oscillates more and cannot convert after that point. And small learning rate, the red line here is also quite slow to convert. So you can see that the learning rate to 0.0003 is good for our model. And I will talk about the fine-tuning the Latin dimension. And we have three hyperparameters, two Latin dimension here, 64, 100, 127, and 256. And you can see the Latin 256 is quite not good. And it is the same for the 64 and 120 but this loss is only in the bottle data set. So to guarantee the performance on other data sets, so we choose the Latin dimension here, 128. Okay, so the third part now I will talk about our resource. And the first one is comparing between the autoencoder and adversarial autoencoder. And we observe that the autoencoder have better performance than the AIEs. And you can see the orange line here is the AIE loss, and it oscillates more and has high loss than comparing with the autoencoder. Okay, so here is some reconstruction image from our model, and here is the couple one. And the first row is the image generated by the adversarial this is from autoencoder, and the second row is the adversarial one, and comparing to the real image which is in the last row. And you can see the image generated by autoencoder is more clear and with high quality. And the same for the Hazelnut dataset. And we will use this image, this reconstructed image to detect whether the image is anomaly or not. And here I will illustrate the reconstruction process, and you can obtain that the autoencoder converts faster and give the better image. Here is in the bottle data set. And one thing that I remind the disadvantage of the autoencoder is that we have no control to the Latin vector. So for the AIE one, because we force it to fit the normal distribution, so we can sampling from the normal distribution and put it only to the encoder, and it can generate the image that look like the input image. And here is a generated build image. Okay, so now we'll talk about the classification and the score map. Sorry, Nguyen. I think you haven't turned on the microphone.
Can you hear me now?
Yes, okay now.
Sorry. So we use the reconstructed image, compare it with the original image to classify whether the original image is faulty or not, and to generate a score map of the faulty pixels. And the accuracy of this system varies between the datasets. For some datasets like bottle and hazelnut like this, the dataset have a few features, so the reconstructed image is close to a good image, and we can generate a good score map like you can see here. It can show us the faulty pixel, the faulty region of the image here and here. However, the score map still shows some distracting lines because the generated image is not close enough to a good image. It is still blurry, as you can see here. And the accuracy of the classification ranges from about 45% for some dataset like carpet and leather to as high as 85% for bottle. And that's our classification score map process. Thank you for listening.
Any question?
Yeah, we have some question here. The first question about the first is the question of Phạm Việt Thành, and he's asked about the another loss or instead of mean square error. Yes, we have a loss that compared to the image and compute the similarity of the two images, and it's different from the mean square error. So it can be used in our project. And a question from Phạm Mạnh Tuấn, and let me okay, try and then encode learn the meaningless Latin. I know the adversarial VIE privacy problem. I'm not sure, but I think now we force the Latin vector to a normal distribution, and we can choose the suitable learning rest. So to have the model can converse. Yes, the question from Fu, from mu and sigma, how to get the value of that? Yes, we use the reparameterized that cast in the VIE. So if you ensure that the gradient can backward regress to the encoder. Oh.
Can you say
yeah,
sorry, say it again about the answer to the question.
The question about the sampling the test.
Yes.
Yes, it is similar to the VIE that we cast in our course, the last lecture, and we use a reparameterized to make sure the gradient can backpropagate to the encoder. Is it clear?
Okay. Right.
And it is similar to the VIE instead of KL divergence loss, we use the discriminator to tell the encoder to output the Latin vector that look like the normal distribution. And the question from that about the filter size. Can you? Actually, we don't have many experience about the Latin the filter size, so I think I have no idea about the question.
We tried a filter size of 3x3 and 2x2, and I didn't see big difference from 4x4, so I keep it that way.
Okay. Inference set of AIE. We explain we know that the AIE have the poorest performance comparing to the autoencoder, so we only use the autoencoder to infer the image effective or not, and the use of AIE is only for the future development.
Can you go back to the slide?
Okay, sir. Let me say, resize my slide.
Slide number 8.
Slide number 8.
Yes.
Yeah.
Could you explain to me the chaining process of that AIE model?
Yes, the first phase is the reconstruction phase. Okay, so let me explain this. It will take the input image to the encoder and output the Z, and the decoder will take the Z and output a reconstructed image, and it will compare with the input image and back propagate the gradient. But in this phase, we don't use a discriminator in this phase. And the second phase is the regularization phase. It means that we will train the discriminator to distinguish the Latin generated by the encoder and the normal distribution. And here we have how to say and normal distribution. We sample it from the and put it to the discriminator, and the discriminator will learn how to distinguish the real and the fake Latin. And after that, we will train the encoder to output the look like normal distribution. Yeah, and we will push it like that. And but instead of the label 0, we use the label 1 here to tell how to tell the encoder how to update the weight to output the look like normal distribution.
What do you mean
normal distribution. You really want it to be like the normal distribution, or what? What is the objective? Is that the objective to make the distribution to be look like normal?
We think that maybe it is better to have arrange the Latin vector to be how to say, but it's our test to see is there any improvement by using the adversarial autoencoder, and we will see that the performance is of autoencoder is better the adversarial autoencoder. Yeah, there is a loss, and also the generated image.
So okay, so let me summarize that the training process for this AE model is like the GAN.
Yes, it's similar to GAN.
So
in the
and you have inside the loop you have training the autoencoder and then the encoder, the discriminator, and then again generator, and then discriminator, like this.
Yes, it's similar to GAN in the discriminator part.
So in what situation that adversarial autoencoder will be better than the autoencoder?
I think it needs more study to future development. But in our project, we only use the reconstructed image to detect the anomalies. So I think autoencoder is better. Okay, so let me see some question in the meeting chat. In boot yes, we set the threshold by to detect anomalies, and the threshold is set by manually.
The threshold is calculated from the model and the training set.
Is this clear?
Yes, it's a learnable parameter, but we didn't design a model for learning it. We just use a function to calculate it.
Okay, so do you have any question?
Maybe we can postpone the continue the discussion in the next lesson because I had another class to do. So okay, let me record the people who participate in the discussion for the group number 2.
Yes, for the presenter we have two, Trần Quốc Khánh and Phùng Hà Nguyễn.
Trần Quốc Khánh. Okay, anybody else?
That's all.
That's all. So who asked a question? Please say your name.
And we see the question from Nguyễn Đức Phú, Lê Trường Giang. Okay, so Phạm Việt Thành, Phan Mạnh Tuấn, and Nguyễn Minh Châu. I think so.
Can you say again? Lê Trường Giang and?
Lê Trường Giang, Lê Trường Giang and Nguyễn Minh Châu.
Okay, so thank you. Okay, so I have to stop here. So maybe we can continue the discussion for group number 2 in the next class. Okay, so
Okay, thank you.
Thank you very much for the preparation and the discussion. See you next week. Bye bye.
Bye bye.